Hi, in this video I'm going to explain this exponential decay application of this kind of model, this A equal to P times E raised to the K times T. And well, let's go to the thing. It says one of the byproduct of nuclear power generation is uranium 233. Uranium has a half-life of 159,000 years. Now, what is this thing of half-life? Well, basically what's saying is that after this amount of years, this number of years, the initial amount you had of uranium will just cut it down to exactly one half of it. So in this case, we have, and we continue here with the statement, is if 120 pounds are produced from a power plant, how long before it degrades to less than 1 pound? Now, I'm going to say something here. If we try to just get directly to this problem, we only know that the initial amount is 120 pounds. So if we try to substitute this on the formula, A of t is equal to P times E to the K times T. I'm sorry, here the P will be equal to 120 times E to the K times T. We will not be able to find what we were requested because we need to find this amount of time required to get less than 1 pound. Because we won't be able to find it because we would still have this K as a unknown variable. So this information, the uranium has a half-life of 159,200 years. It's actually what we need to find the K. So well, how this works, the half-life thing. Well, basically what this is telling us is that every time that these years are gone through, let's say we had originally 120 pounds. After exactly 159,200 years, you will get exactly 60 pounds. If again this same amount of time passes through, we will have 30 pounds. And every time you will get just half of it, and it will just continue. So we can use this information to find out something. So we know that after these 159,200 years, we know that I'm going to write it here. After this 159,200 years, the amount of uranium-233 will be equal to 60 pounds. 60 pounds. So we can use this information to find the value of K. Let me show you how. We get would be in this case 60. It's too big here. I'm going to use actually a different color just to make this notice I'm doing something different. 60 it's equal to 120 times E raised to the K, and we know that when this gets to 60, the time will be 159,200. So it will be times 159,200 over here. Okay. Now we have to simplify this out. We're going to divide both sides here by 60. There it is. Now we can simplify this out. I'm sorry, I want to divide by over 120. 120 has to be be 120, 120, and we'll get here, this will cancel out, this will cancel out, it will get 1 over 2. So we get to this statement will be 1/2 is equal to e to the 159,200 K. So if we want to solve this out, we have to apply the natural log on both sides of the equation. So it would look like this. Natural log of 1/2 would be equal to the natural log of e to this insanely big power. But by using the natural log, we will cancel out these two and we'll just have this. Natural log of 1/2 is equal to 159,200k. Now we can just divide both sides of the equation by 159,000k, 59,200k, and we'll get to this. The natural log of 1/2 over this number, and here I'm going to use a calculator to get the value of k. So let's see, it will be the natural log, let's see here, natural log of 1/2, there it is, over 159,200 years, and this would be a insanely big, a small number. It will be k, it's equal to negative 4.3539 times 10 raised to the -6. There it is. This is a super small k, and the thing here is this has this negative number because we are representing here a decay. The amount of objects, the material is going down. It's not increasing. It's decreasing. So here we already got k. So the only thing remaining here it's to solve for t. Now here there's a kind of tricky question, because how long before it degrades to less than 1 pound? Here I would say that the final A of t will be just equal to 1. Let's say it's just equal to 1. So once we get to 1 pound, the question here is, what would be the value of t? Well, it would be here, t. I'm going to write k with this yellow just to sign that it's the one we already found here, because I don't want to write this long number all along. So it will be k times t, and we have to solve for t. So we are going to isolate this variable. So we're going to divide both sides by 120. We'll get here simplifying out. We'll get to, it's 1 over 120 equal to e raised to, again, k. I'm going to use this yellow color just to sign this one we already found, times t. And I'm going to apply again here this natural log on both sides. The natural log of 1 over 120 is equal to a natural log of e raised to k times t. And here we're going to cancel out again this natural log and e, and we'll get to the natural log of 1 over 120 equal to k times t. K times t. And then we have to solve for t. So t will look like this. It will be the natural log of 1/2 over the value of k, that it's actually what we found, will be -4 times 0.3539 times 10 to the -6, which is a very small number. I'm going to just move along this line here, and then by solving this out on a calculator, it will look like this. I'm just going to write it down here. It's a natural log of 1 over 120 divided by this k, and we got the result for t would be equal to 1,099,576.98 years. So it's a pretty long amount of time, but I think it makes sense because we can just say here that every time that these 159,200 years passes through, you will get a smaller and smaller amount of uranium-233. So I guess it makes sense that it has to pass all these more than 1 million years in order to have less than a pound of this uranium-233. So, well, basically that would be all with this example. Hopefully it was useful for you.